All right. First of all, thank you to Cody and John for organizing this wonderful series. This talk is based on various works with Mackie Kim, Cody Long, my advisor Liam McAllister, Jacob Morris, Mike Settleman, and Andreas Röstascom. So the subject of this talk is compactifications of string theory on Calabi-Yau manifolds with a large number of moduli. But before I get to that, I want to take a step back and ask two questions. Question one: what is possible in quantum gravity? And question two: what is generic in quantum gravity? A particular way to answer the first question is to show that something is possible by exhibiting it in a solution of string theory. And the second question, I don't know how to answer in full generality, but there are certain corners in quantum gravity where we can answer it. And one such corner is decoupled compactifications of string theory. So to get started in answering these questions, one can study compactifications on simple Calabi-Yau manifolds with only a few moduli. This is a very valuable lamppost, and over the past few decades, it has been a great source of knowledge. The problem is that this is only an exponentially small fraction of the landscape. The number of Calabi-Yau manifolds increases exponentially with H11, and the number of flux vacua increases exponentially with H21 in type 2b and H31 in F theory. And the goal of this talk is to replace the lamppost with something more powerful. In particular, I will describe a research program where we construct Calabi-Yau manifolds with large Hodge numbers and study compactifications on them. So this is the outline of the talk. I will first describe how we make these Calabi-Yau manifolds. I will then move on to the geometric data of holomorphic cycles and describe a particular application regarding ultralight axions. And then I will move on to periods of 3 cycles and discuss how these methods pave the way towards an explicit construction of a KKLT vacuum. In this talk, I will focus on threefolds, but most of what I say will also apply to fourfolds. Right, so the largest known set of Calabi-Yau threefolds are hypersurfaces in toric varieties. To construct such a hypersurface, we take a 4D reflexive polytope, where reflexive means that the only interior point is the origin. In the picture, I have a 2D example, and then we obtain a suitable triangulation. This defines a polyhedral fan, which defines the variety V that has a Calabi-Yau hypersurface X. So in 2D, we have only 16 reflexive polytopes. In 3D, it's over 4,000. In 4D, it's over 400 million. Here's a heat map where the x-axis is H11, the y-axis is H21, and each dot is a particular polytope. The largest of these gives rise to Calabi-Yau manifolds where H11 is equal to 491, and its dual gives rise to H21 equal to 491. Even more importantly, though, the number of triangulations per polytope increases exponentially with H11. So a natural question to ask is, well, how many Calabi-Yau hypersurfaces are there in the set? No one knows, but recently we wrote an upper bound of 10 to the 428. Let me move on to holomorphic cycles and set some notation. So V is the ambient variety, X is the Calabi-Yau hypersurface, and the Maury cone is the cone of effective curves. The Kahler cone is the cone of Kahler classes, and these two cones are dual to each other. The Kahler cone can be defined as a set of one-one forms where all effective curves have non-negative volumes. Computing the Maury cone of X is hard. It can only be done in some cases, and there is no general algorithm for computing it. We can compute the Maury cone of V, however, which contains the Maury cone of X, and that is sufficient for most purposes. The volumes of effective cycles depend on the Kahler form J and the intersection numbers. And finally, I will define a stretched Kahler cone as the region inside the Kahler cone where all effective curves have volumes at least one in string units. So this is the Kahler cone. And this interior region is this stretched Kahler cone. It's an estimate of the region where the broadsheet instantaneous expansion converges and the alpha prime expansion is under control. It will be useful later on. So to recap, to make a Calabi-Yau manifold, we need to take a reflexive polytope, obtain a triangulation, and then at the very least compute the intersection numbers. And these computations can be done using math software like Sage. And in the regime where H11 is order 1, there are a large number of studies. I could not fit all the citations here. My apologies. If we go up to 30, we have only a few. And only recently, we can access the regime where it's order 100. H11. These computations get expensive very rapidly. For example, at H1 of 491, we have to compute millions of intersection numbers. over the past few years, we've developed algorithms to perform these calculations efficiently. And to give you a sense of the improvement, in 2014, we could obtain a triangulation only up to H1 of 25. And it took a very long time. And it also did not work in some cases. We can now go all the way up to 491 and obtain a triangulation in a tiny fraction of a second. Similarly, for computing intersection numbers, in 2017, we could go up to 100 or so, and it took a long time. Now we can go up to 491, and it only takes a few seconds to compute all intersection numbers. We put all of these tools inside a software package, which we call CYTools. And in particular, CYTools can construct the Calabi-Yau manifold and compute the intersection numbers in 4 lines of code. So it's easy to use. It can compute a number of other things like the faces of the polytope, the Stanley-Reisner ideal, the Demore-Cohn of the ambient variety, and so on. And importantly, it can perform these calculations much faster than, say, Sage. As an example, we can compute the intersection numbers 10,000 times faster than Sage. So we hope to make this available in the next few months. I also want to mention that some of these quantities can be predicted using machine learning. So we achieve this using a deep neural net. In particular, it can compute the volume of the Calabi-Yau, even at H1 of 491 with high precision. And importantly, a single prediction takes only 50 microseconds. So this is a speed up of another factor of 10,000 compared to CYTools. So now that we have all of these tools, let me describe a particular application. Our goal is to answer the question, what is generic in the Calabi-Yau hypersurface landscape? What we will do is that we will construct ensembles of Calabi-Yau manifolds and compute the topological data. And then we will seek to detect patterns in the data. And once we do so, we will study the consequences in compactifications. One such pattern is that at moderate and large H11, the Kahler cones are extremely narrow. As a result of this, the stretch Kahler cone is far away from the origin. So this is the stretch Kahler cone. If the Kahler cone is narrow, it gets pushed away from the origin. So if we pick a Kahler form inside the stretch Kahler cone, the volumes of effective cycles are now extremely large. This has a number of consequences. I will describe one. Consider type 2b compactified on an orientifold of a threefold hypersurface X. The C4 axions get their potential from non-perturbative objects wrapping 4 cycles. And the potential is suppressed exponentially in these volumes. So if the 4 cycles are large, the potential is suppressed and the axions are ultralight. If these axions exist in our universe, they could be observable via black hole superradiance. Viraf is going to say much more about this right after me, so I won't get into it here. There are a number of other consequences. For instance, because the 4 cycles are so large and the volumes are so different, it is not easy to make these non-perturbative contributions compete to stabilize the Kahler moduli. So realizing the KKLT mechanism is hard. It was recently shown by these authors that the same pattern results in 7-brane dark sectors in compactifications of F theory. And also the patterns in the volumes have implications for fitting throats into compactifications. So far, I have discussed the geometry of the Kahler moduli sector and described a particular application. Now let me move on to the complex structure sector, and in particular discuss how to compute the periods of 3 cycles, which we need for flux compactifications. We start by picking a basis of A and B cycles as usual, and then the periods are defined as the integral of the holomorphic threefold over these cycles. These periods can be expressed in terms of a pure potential F. So our goal is to compute F. Around the large complex structure point, an expansion into a polynomial part and an exponential part. And to compute the periods, the most important step is to identify an integral basis of 3 cycles. In general, this is hard to do. In this case, however, we can make use of mere symmetry, which maps integral 3 cycles in X to integral even the dimensional cycles in the mirror of X, X tilde. In fact, this is reflected in the expression for F, where the coefficients in the polynomial depend on the geometric data of holomorphic cycles in X tilde, and importantly, we can compute them. Let's move on to the exponential part. It is a sum over effective curves in X tilde. So it requires information about the Morricone of X tilde, which we have. And the coefficients in the sum are called the genus 0 Gopakumar-Vafa invariants. Using the methods existing in the literature, one can compute these invariants only up to h to 1 of 5 or so. And also most of the results in this the direction require that the Morricone of x tilde is exceptionally simple. Over the past year, we have improved these methods significantly, and now we can compute these invariants systematically when h to 1 is order 10, with no requirements on the Morricone. And for some curves, we can go all the way up to h to 1 of order 100. Okay, so now that we can compute volumes and periods of cycles, let me move on to perhaps the most exciting application, is the de Sitter space in the swampland. Our ultimate goal in this direction is to explicitly construct the de Sitter vacuum using the KKLT scenario. So our KKLT requires 4 ingredients to exist in the same compactification. An exponentially small flux superpotential, a strongly roped throat, non-perturbative corrections, and anti-D3 planes. In this talk, I will only discuss the first 2 items. Let's start with item 1. It was argued by Denef and Douglas a long time ago that superpotentials should exist. Until recently, though, the best examples we had were roughly of order 10 to the minus 2. In a paper last year, we gave an algorithm that depends on the holomorphic data of x tilde and returns a small superpotential. We gave an example, where it's 10 to the minus 8. So item 1, check. Item 2, strongly warped throats exist. The question is, can these 2 items exist in the same compactification? In a paper that came out 2 weeks ago, we showed that in some cases, it is possible to analytically continue to a vicinity of a conifold point, and then use the same algorithm as we did before. And also to produce an example in this paper, we obtained orientifolds at H11 of order 100 and gave a method for that. So it's a nice bonus. Independently, Blumenhagen, Alvarez Garcia, Brinkman, and Schlechter use the same algorithm and obtain a different example. So item 2, check. Ultimately, I hope that constructions of this sort will inform the discussion around the tester solutions and string theory. So let me conclude. We can efficiently construct Calabi-Yau threefolds with large Hodge numbers and compute the topological data. We put some of these tools in a software package, which will come out in the next few months. These tools enable a large number of applications. I described two examples. At large H11, the Kahler cones are extremely narrow, and as a result of this, we get ultralight axions. And also, one can use these tools to obtain small flux superpotentials in the vicinity of strongly warped curves. And ultimately, this is a new part of the landscape. So we don't know what we'll find, and as we dig deeper, we will surely encounter new surprises. Thank you for your patience, and I can take questions.
All right, Mehmet, thank you for the very nice talk. We can all thank Mehmet using our clap emoji. Looks like we have several questions immediately. The first one is from Laura.
Very nice talk. Thanks very much. I wondered if you could just say a little bit more about how you're able to achieve this computational speed up at high H11 for the triangulations.
Sure. So let me go down to where I had the picture of a triangulation. Ah, there it is. So one can obtain a triangulation is to take all the points and lift them up into one higher dimension. So once we do that, I can take the convex hull of the resulting object, and that defines a triangulation because the faces of that are for generic heights simplices. It turns out that that operation is much faster than constructing a triangulation first, and then making sure that it is regular. To give a little more detail, we found a software package called Segal, which people use for computer graphics, and it turns out it can do this operation very fast.
Cool. So the claim is that you're really doing all 19 billion triangulations at high H11 for when you're. I mean, so I guess I'm asking, when you're determining the Kahler cone, you're not just picking one triangulation and finding the Kahler cone of that. You think you can do all of them?
Oh right, we do. So let me go to the slide where I had the times. At H1 of 491, there's an exponentially large number of triangulations. So obtaining all of them is impossible.
That was my question. Yeah, that seems very impossible.
Right. That is impossible. This is for a single triangulation. We can obtain a single triangulation
for each one. Okay, thank you.
Yeah.
All right, our next question is from Yunan.
Hi. So I also have a question about the large H11. For the particular one with the 491, and so I think for that one, the Calabi-Yau threefold is actually non-favorable, because if you consider an elliptic vibration, then on the base there's some -11 curves. So basically, there could be a point in the ambient toric fourfold which corresponds to a reducible divisor. So is that true? And also, if that's true, then I wonder how do you compute the true intersection numbers for the non-favorable cases?
Okay, so it is actually favorable as defined by Batyarev, meaning that all the prime effective divisors in the ambient variety correspond to irreducible divisors in the Calabi-Yau. Even if they were not, though, it is not that much harder to compute the intersection numbers because you basically get extra copies of the divisors, and the intersection the numbers for these extra copies are basically identical. Does that answer the question?
Well, I was just wondering, like, if a point corresponds to a reducible divisor with two components, then how do you compute the intersection numbers between those two components? Is that also straightforward?
Let's see. Okay, that's a good question. I'm not sure off the top of my head, but Cody and the Damon and the Brown and Ben Sang, I think, have a paper from 2017 where they discuss cases like this. So that might be a useful place to look.
Oh, okay.
Yeah, let me not comment on exactly the full picture right now, but I think that's very doable. All right, our last question is from Wadi.
Thanks. Very nice talk, Mehmet. This is great stuff you guys are doing. I actually have two quick questions. The first one is, you said it's hard to get the periods when H21 is large. And wasn't there this work of Clem a number of years back, Clem and company, where they gave a general methodology that should work for a general elliptically fibered Calabi-Yau, which might apply in these contexts? And the second, I'll just ask the two questions. And the second question is a little bit related, which is, as Yinan said, this particular H11 equals 491 case is elliptically fibered. And so something which actually Cody and I know Cody and I and others had discussed off and on at times in the past, if something is elliptically fibered, you can imagine using the elliptic fibration to do a kind of a modular triangulation where you triangulate each of the basically curves on the base in an independent way, and then you just take a product of those different triangulations. So I'm just curious whether you guys had played with that, or whether that fits into the way you're doing it, or whether you just haven't integrated with that perspective.
All right. So let me get to the first question first. So in the way we computed these periods, the difficult step was not to just compute the pre-potential, but to identify an integral basis. And for that, we needed an integral basis in the mirror, and that's how we could do it. So I'm not sure whether there are alternative ways to do this, to compute the periods.
Yeah, I thought somehow that the stuff that Clem and others had done, which only works for elliptic Calabi-Yaus, but those seem to be most of them, that seemed to be a general methodology that would give you a basis and period. But to be honest, I've never fully understood that paper, and I haven't looked at it in a long time. So I don't know, maybe somebody else here has some comment, but okay, thanks.
That is useful, thanks. Let me move on to the second question. Right. So in short, we did not. But it has been on my to-do list to find elliptic fibrations in these things for a long time. And in particular, I think I might be able to implement an alternative way of finding them by identifying Kahler divisors. So these will correspond to particular triangulations, and it might be possible to search in the secondary polytope to go find them. And I wonder what would happen if one did that, if the results of the two algorithms would match. But yeah, this is a very interesting question.
Good. Okay, thanks.
Mankey, really quickly, one comment?
Yeah, about Clem's paper on the elliptic fiber. In the very series, in the series of very nice papers by Clem, they studied the Picard-Fuchs equation in the case where Calabi-Yau has elliptic fiber. But the deal is that for the elliptic fiber, you can easily determine the Picard-Fuchs equation, hence the integral basis. But for the rest of the devices or some curves, you still need to do the very hard work. So it was still a very challenging problem, and then we're giving out a more general method that could just compute the principal parts of Picard-Fuchs without knowing any details of the vibration structure.
Thanks, man.
All right, I really must cut this off, but let's do one more quick question from Alessandro.
Yeah, I'm sorry. I want to come back a little bit on the speed of the program. You said that now you can compute the Gopakumar-Vafa for without the use of the Morricone, and instead of how Ozono and Clem proposed in the 94, and in those papers, you needed to solve the Picard-Fuchs. After you need also to invert the solution, and then you need to extrapolate the intersection numbers, and those usually are very tedious and very computationally expensive processes. Do you renounce completely to use the Morricone, and so you have a faster way to solve the equation, or maybe to find the Gopakumar-Vafa? So you use a different method to the Ozono-Clem, or is still related?
Okay, so first, this is new, so it is not included in CYTools.
Okay.
And second, we do use the Morricone. That you need because you need to identify the effective curves. The statement is that we don't put any conditions on the Morricone. As in, we can take a random Calabi-Yau with whatever cone and then work with that. In particular, it does not need to be simplicial. It can have a large number of extreme arrays.
And you have a very efficient way to invert the solution, and then to match the power series in both sides and to get the intersection numbers. So you have improved the Ozono-Clem code and to accept non-simplicial cone, and also to speed it up because the program was very slow when you go high. Okay.
Yeah, pretty much.
Good. All right. We really need to move on, but thanks everyone for the really nice discussion. And thanks Mehmet again for the really nice talk.